Air column. So let's hash out the vocab on this. I've got a type of resonating air column that's open at one end, it closed at the other, and here I've drawn it kind of like a toilet paper roll. Can you see what I'm talking about? But I capped it off at one end, and I'm trying to indicate that it's closed at one end with a shading on the end. So this is what I call a closed-ended air column. My good friend, another physics teacher, calls it an open close, and I think you see where the name would come from. So this is closed-ended because it's open at one end and closed at the other. And the fact that it's open at one end and closed at the other means that air pressure is free to fluctuate. Only at the open end. Fluctuate. F-L-U-C-T-U-A-T-E. Fluctuate. Only at the open end. Now, of course, if there's an air column that's open at one end and closed at the other, there's also one that's open at one end and open also at the other end. And we call this one the open-ended air column. And that same physics friend that I have calls this one the open-open. Anyway, it's uncapped at both ends. Not covered at either end. And what that means is that air pressure is free to fluctuate at both ends. Nice. So I want to approach this idea of the closed-ended air column first. With a closed-ended air column, and I actually just demonstrated, in real life, IRL, in the lab area with a closed-ended air column, and you can probably see some videos online for closed-ended air column harmonics and resonance. Very YouTubeable to find these videos. So I'm not going to try and pull up a simulator or something. It seems that when I pull up simulators, I seem to get my audio knocked out on these videos. Okay, so I'll share a video through the online platform and we can see it later. Okay, but for now, let's just talk about the fact that for a closed-ended air column, and I'll just cap this off. I'll just label that this is closed. A closed-ended air column is allowed to have its air pressure fluctuate at the open end. And so this arc is meant to show that the air pressure goes high and then it fluctuates low. See how this is almost like a graphical representation of a sound wave. So rather than stippling and showing high and low pressure variation with a stippling effect, we're showing it with this kind of wavy type graph way of illustrating. Okay, so then we would say, well, at the mouth, if we get maximum fluctuation, another word that we've used for that in the past is constructive interference. And so constructive interference will always occur at the open end and never at the closed end, at the open end of any air column. So, and if I look at this, you guys can see, if I have a wave, here's a wave. You don't have to draw this wave. I just want to have it as a representation on the page. Here's my principal axis. If I have this, it starts from 0 and it goes up to a peak. What fraction of a wave have I drawn? Options are whole, half, or quarter. What is it? Not a half. It's a quarter. Look, I only went this far. You see that that's just a quarter from 0 up to a peak? This is a quarter of a wave. So if a quarter of a wave is introduced into a closed-end air column, we say that a standing wave pattern consisting of a pressure antinode. Look, this is a node. We've talked about nodes and antinodes. This is an antinode, maximum fluctuation, right? A a pressure antinode at the open end of the air column will be established in the tube. Now, as I look at this, I say, oh, look at that. Somebody's already drawn. That would be the first harmonic, because that's the first frequency at which you could get an antinode and a node to form. Okay? Now, unlike the string, notice that this one's not symmetrical. It's lopsided because the tube itself is lopsided. That makes sense. It's almost like I have a string that's fixed at one end and unfixed at the other. But it's not a string, it's air, right? So this air is unfixed, which means it can fluctuate at one end, which makes sense in the context of a musical instrument. You know, you could blow across. Anybody ever blown across a pop bottle before? You know, like you take a pop bottle and you blow across the pop bottle and you make like a hoo, hoo, hoo kind of thing. What you're doing when you blow across that pop bottle, here's the pop bottle. Oh my gosh, I can't believe my pop bottle is such a terrible pop bottle. You imagine the pop bottle by nature is capped off at one end because I don't want my drinks to fall out. The opening is the open end. So when I blow across the pop bottle, I'm getting this effect, fluctuation at the top. Anybody ever taken a pop bottle and you blow really hard? And you start off going hoo, 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 and then you blow hard and you go hoo, and it jumps up. It's like the frequency jumps up on that pop bottle. Try it. Next time you get a glass pop bottle or something. Glass works better than plastic for me. But what you actually do when you're blowing really hard is you're popping it up to the third harmonic. So the third harmonic looks like this. Fluctuation at the mouth, but counted off. If this one here is the antinode, this is a node, this is another antinode, and this is another node. Look at this. How many, or I should say, what fraction of a wavelength is this? Raise your hand if you think you know the answer. Yeah? 3/4. Yeah, this is, or I could say it's 3 lambda over 4s. But 3/4, it's 3 lambda over 4s. This one over here, from start to finish, was only 1 lambda over 4. Or I could write it as 1 times lambda over 4. Now, as I'm writing this 1 lambda over 4 and 3 lambdas over 4, can you guys see a connection with the harmonic number already? You see what I'm talking about? Somehow the harmonic number and the number of lambdas over 4 probably are connected, because we've kind of been down this pathway with strings. Now with strings, it wasn't the harmonic number times lambda over 4. It was the harmonic number times what? Yeah?
Lambda over 2.
Yeah, lambda over 2. And so it turns out for closed-ended air columns, quarter wavelengths figure prominently. When it comes to strings, half wavelengths figure prominently in our thinking. And so I'm just kind of putting that out there right now. Anyway, since the frequency of this harmonic is 3 times the frequency of the first harmonic, and people say, well, how would you know that the frequency is 3 times? How about this? If I cover up this, can you guys see that this quarter wavelength is 1/3 the length of this quarter wavelength? And if the wavelength is did I say quarter? Yeah, no, I said a quarter. This quarter wavelength is 1/3 the length of this quarter wavelength. 1/3 as long a wavelength is going to mean 3 times the frequency. And again, we kind of been down that pathway before, because we're assuming that the waves can travel at the same speed up and down these air columns, right? These air waves can travel up and down the same speed. So if speed is a constant, if I decrease the wavelength by a factor of 3, that means I'm going to have to jack up the frequency by a factor of 3. True? Because the speed stays the same. So that means that the third harmonic is 3 times the frequency of the first harmonic. And this is called the third harmonic. All right. Now, in terms of equations, because everybody likes to throw in the math here, we say that F3 is equal to N times F1, where N equals 3, because N is the harmonic number, okay? F1 is the first harmonic, or the fundamental frequency, or the natural frequency. We talked about those synonyms before, right? And so we say that means that F3 is going to be equal to 3F1. No problem, okay? Oh, I guess I did make a little mistake. I meant to write the general equation, and I jumped right to writing F3. So this is F sub n for the general equation, and specifically F sub 3 for the third harmonic. All right, there's this follow-up question, because so far I did the first harmonic and the third harmonic. What about the second harmonic? Why the heck did this guy skip it? So unlike other instrument types, there is no second harmonic for a closed-ended air column. And let's think about this. For the first harmonic to occur, I would have to be making some noise. Maybe I'm blowing across a pop bottle. Maybe I'm blowing on the mouthpiece of a musical instrument, but I'm making noise. I'm causing fluctuations of pressure, and those fluctuations in pressure are going to cause the resonance to occur. In the case of the demo that I did at the beginning of the period, I had a tone generator on a phone over top of a glass tube. Again, I'm fluctuating the pressure at the mouth of that air column. All cool? But what about this? If I want to have an even harmonic, here I'm going to draw the cylinder, so you draw yourself like a toilet paper roll. An even harmonic would look like this. Remember, first harmonic is 1/4 wavelength fitting in. The second harmonic, by extension, would mean that I'm getting 2/4 wavelengths to fit in. Notice here, I'll split this in half to make it really easy to see. Can you guys see that there's 2/4 wavelengths there? And if this were to happen, I would have a node at one end and a node at the other end and an antinode in the middle. But what I would be talking about here, if I was going to get a second harmonic to occur, is I would be hoping to create resonance by not making a noise at the mouth. Can you see how that's physically silly? Like, oh, I'm going to make resonance by not saying anything.
What?
Yeah, exactly. What? That's kind of dumb. It just is. And you say, well, what about if we did another even harmonic? What if we did the fourth harmonic? Okay, no problem. I can do that. Another toilet paper roll. This one, if it's the second harmonic, here, I'll write 2 lambda over 4s. If I wanted to do 4 lambda over 4s, it would look like this. Okay? And again, I can break this up to say, hey, look, quarter wavelength, quarter wavelength, quarter wavelength, quarter wavelength. Yeah, there's definitely 4 quarter wavelengths there. But again, I'm talking about having a node here at the mouth, and sure, this is capped off at one end. But again, I'm talking about trying to produce resonance by not stimulating the air inside, by not producing a sound at the mouth. And I don't expect to make a musical note by choosing not to blow across my pop bottle. That's physically stupid. Doesn't make sense. And so for that reason, the fact that we'd be talking about having no stimulation at the mouth of the air column to cause this resonance to occur, we say that it's physically not meaningful. Okay, so in the end, what that means is that there are no even harmonics. So let's complete filling in the blanks here. It says the next frequency above the fundamental frequency is the third harmonic. Okay, that third harmonic. And we drew the third harmonic already. It's right here. And then point 3 says, in fact, a closed-end instrument does not possess any even harmonics. And I'm hopeful that I've sold you a little bit with this idea of the second and fourth harmonic not making physical sense. We don't have any even harmonics possible. And so as a consequence, that means only odd harmonic numbers are produced, where the frequency of each harmonic number is some odd number integer multiple, and I made my blank too small, some odd number integer multiple of the frequency of the first harmonic. And remember, we're playing around with synonyms here. So first harmonic or fundamental resonance frequency or natural frequency. These are all synonyms that you might see floating around out there, okay? But the first harmonic. I'm going to try and lean on the number system as much as possible, but you need to be able to interpret the non-number way of talking about that first harmonic. Anyway, for this reason, the frequency of the fifth harmonic, and here's an illustration of the fifth harmonic for a closed-ended air column, is how many times the frequency, do you think? Yeah?
5.
5, yeah. 5 times the frequency of the fundamental frequency. Or natural frequency. Or first harmonic. And I know it's tiresome for me to use all of these synonyms, but I want to make sure that I really drill it in so that it makes sense to people, okay? Because I hate that there's so many different words for the same thing. All right, so when it comes to doing the equations, I'm not going to belabor this too much. You guys can see that if all of these air columns were the same length, what we're saying is that the length for a particular air column, and I'll write n before on the bottom right of this L just to emphasize that we're talking about an integer thing here. The length of the air column is always going to be equal to, when resonance occurs, it's always going to be equal to n, an integer, times lambda over 4. This is specifically for closed-ended air columns. Notice that it's different than for fixed-ended strings. And we talked about the geometry for why it's different. Where n is an odd integer. It cannot be anything other than odd and always positive. And that n value, somebody asked me in the other class, asked me if the n value contributes to the significant figures. It does not. Integers never contribute to significant figures. We're just counting how many. And you either had a whole thing of that thing or you didn't. So it doesn't impact the significant figures when you do our calculations. And what's more, the harmonic frequency, f sub n, is equal to n times f1, the first harmonic. So really, let's spell it out. I have a sentence for it, but I'm just going to spell it out. N is equal to 1, 3, 5, 7, 9, dit. Okay, odd integers. Does anybody have any questions about this? Anybody? All right. Well, yeah, I want to take a look at. Yeah, we did. I want to take a look at this. Every once in a while, I have somebody say, "Oh, I saw this equation that said this: Fn is equal to 2n minus 1 times f1." Let's just take a quick second to investigate this, because this is an equation that I see online. And the person that asks me this question inevitably says, well, the internet says that n can take on values of 1, 2, 3, 4, 5. This is what they say to me, okay? Let's do a quick investigation into this. If n is equal to 1, wouldn't that be 2 times 1 minus 1? 2 times 1 minus 1 is equal to? If n was equal to 2, 2 times 2 minus 1 is? 4 minus 1 is 3. 2 times 3 minus 1 is? 5. Can you see that this little bracketed expression here is a mathematical machine that generates odd numbers? It's just a math machine that generates odd numbers. And so the reason I don't like this equation is because these n values, 1, 2, 3, 4, 5, are not the harmonic numbers. What is the harmonic numbers is the product of that little binomial. Do you see what I'm saying? And so I'm not saying that this equation doesn't work. What I am saying is that the n value here is not the harmonic number. It's just an integer count, okay? So I'm going to avoid this equation, not because I think that it's wrong, but because it confuses the point about n values being harmonic numbers. If we stick with only using n values being odd and recognize you can only use an odd number, then the n value is always going to be the harmonic number, and the harmonic number is going to let you know that the third harmonic is 3 times the first harmonic. And we won't do any funny business, okay? So this is really just me trying to look out for you, and I'm presenting this equation not because, we got something that I'm trying to cover up or whatever or say is wrong. I just want to make sure that, yes, I'm aware of it. You can be aware of it too. If you happen to see it in people's online solutions, just know what they've done, okay? We shouldn't be afraid of other ways of doing things. I just have my own preferences for my own reasons.